Hi everyone, so in this video we are going to look at induction motor construction, and by now you should have gone through the video with the 3D model, and you should have a good idea of how it operates and so on, but we'll take again another look at the construction of the machine. So by the end of this session, you should be able to describe the construction and operation of a three-phase induction machine, and you should also be able to distinguish between wound rotors and squirrel cage motors. So just to begin, induction motors, as you all may know if you have ever spoken to anyone in industry about the kinds of motors they use, these are very common and they account for over 90% of the machines you have in industry. They often call it the workhorse of the industry. The stator is a three-phase distributed winding. So before we did the DC motors, and those on the stator we simply had a coil to give us a field. We had the field winding on the stator with a DC current. So the induction motor is an example of an AC machine. It is sometimes called an asynchronous AC machine, and you'll find out why it is called an asynchronous machine as we go along. The stator is a three-phase distributed winding, and this can be connected in star or delta, and just like your normal other three-phase things. And the rotor could be either a distributed three-phase winding, which we call a wound rotor, or a cage of interconnected copper bars, which we call a squirrel cage rotor, although it's more like a hamster wheel, as you'll see. So why is the induction machine preferred? Well, we have a simple and rugged construction. There's a low cost and minimum maintenance, and we'll see why as we go along, as we go into the construction of it. And there's high reliability and sufficiently high efficiency. So there are two parts that we have to describe. One is the stator and one is the rotor. So the stator of the induction machine is energized obviously through the stator windings, and the orientation of these windings is what is important. We have three phases spaced 120 degrees apart electrically, and we want to orient them in the core, on the stator, so that we produce a uniform rotating magnetic field. So here we have that visualized. We have A and A prime, or N in this case, B and C. So we have these three windings that are all wound. The axes of the windings are at 120 degrees to each other. So we have the three windings they are oriented 120 degrees apart, and also the voltages and currents that go into them are electrically 120 degrees apart. So they're spaced 120 degrees apart this way. And also you'll notice that A, B, and C are all different values here. And that is because if you look at where they are on the waveform, I don't know how accurate this will be. If you look at where they are on the waveform for any particular point in time, you're going to get different values. So this is the two ways that the waves are separated. Physically, the windings are 120 degrees apart. When we say the windings are 120 degrees apart, if you have a coil this way and you have a coil this way, the axis, the normal to the plane of the coil is separated by 120 degrees. And the currents and voltages in that coil, if we plot them, they would be 120 degrees apart. So they're separated in two ways, and that is very important, as we will see. So this is just a summary of what I just mentioned. And if we look at what this means mathematically, we will see that the flux, which we could describe sinusoidally, this is the scalar flux, if you will, is phi m cosine omega t, and you should remember scalar field and vector field, the scalar electric and the vector electric side from ECNG 1015. That is not something I usually discuss, but if you want to relate that to what we are doing here, this is what it means. The scalar electric part refers to the voltage or current waveform, which gives you the flux, and the vector part is the direction of orientation. So so here we have three fluxes which are generated by the currents in each winding: phi m cosine omega t, phi m cosine omega t minus 120, and phi m cosine omega t minus 240. And then we have each one of the windings, this one, which is this phi an, is this entire equation, is at a displacement of 0 degrees. Phi bn, which is here, is displaced by 120 degrees, and phi cn is displaced by 240 degrees. So what I'd like you to do now is find the resultant flux, which is the sum of these three. And to do that, you could make use of this equation here, this identity, and find out what is the resultant magnetic flux distribution. And I would like you to bring that to class so we could discuss it. So that is talking about the magnetic flux distribution, and we said that these are due to the winding configuration. So let's look at how these are wound particularly. So we have each phase is spatially divided into poles. So just like we had in our DC motor poles, we also have poles in the induction motor. And below in these diagrams, I'm showing you the simplest case, which is one pole pair per phase. So phase A, phase B, phase C. One pole pair per phase. And the way this is wound, you'll see, is like a solenoid. So you come in with phase A here, and you're winding it around like this, and it's just like you continue the winding. So imagine if you had a solenoid and you just pulled it apart in the middle and separated the middle, and that is what you would get. And the reason you want to do that, if you remember your right hand grip rule, let's assume current is coming in this way. Then what we want to create, if you use your right hand grip rule, you'll get a north pole, a south pole, a north pole, and a south pole. So you'll have south here and north here. So we want these poles to be opposite. If we wrapped it the other way, then the current would go, say when we got to this point here, instead of going around the back, if we came around the front and the current went this way, then what we would end up with is north here and south here. So we don't want that. We want to have opposite poles on the adjacent windings. So this is for the simplest case of one pole pair, and I said opposite poles on adjacent, on the adjacent poles for the phase, and I purposefully did not say on the opposite poles, as you will see when we look at 2 poles per phase. So this is 2 poles per phase now. So you'll see for phase A, which comes in here, the current enters here, and then I wind the coil this way, and then I go to this side here. Now what I want is north, south, north, south. So I want the poles to be alternating around the machine. Notice I have north on both sides. So it doesn't matter that they are opposite to each other. What matters is that I have a north and a south, north, south going around the machine. So I want to make sure if I use my right hand grip rule that you see here, if I look at the winding direction, then the north pole will be here. If I look at the winding direction, so I'll have north, south. If I look at the winding direction here, I'll have north, south. If I look at the winding direction here, I would have north, south. And here I would have north, south. So I want to wind things in a way that I have these alternating polarities. So if I look at the magnetic field will go like this. The magnetic field will go like this, as opposed to the first case where we'd have the magnetic field here, I think was south and north, just going across like that. So I just want to take this section and bend it down 90 degrees here, so the field ends up like that. So that is how I want to orient the coils in my machine. So that is the stator orientation, and now we'll talk about the rotor orientation. And the first one we want to look at is the squirrel cage rotor. So here is the stator. What I want to look at really is what goes inside of that, the rotor. So the construction is to have these thick bars going down the rotor, and then on the end here there is a circular plate which connects all the bars together. So if we look at it, you'll see that we have the bars here and then the plate around the connecting them on each side. So all the bars are short-circuited together. And just like in the transformer, to direct the magnetic flux, to concentrate the magnetic flux and make the system more efficient, we put in a cast iron core, so or a soft iron core. So the bars would go through here down to each end, and then the plate would be around here. And similarly, you'll have another plate on the other side. And that is basically the squirrel cage configuration. And they call it squirrel cage, of course, because you would have some little squirrel inside here running on the treadmill. And that's why I say you could usually, but to me it's more like a hamster wheel than a squirrel cage. So nobody calls it a hamster wheel, everybody calls it a squirrel cage, so that's what we're going to call it, although it really looks more like a hamster wheel. Anyway, the next thing we want to look at is the wound rotor. And the wound rotor, all we're doing now is, instead of using solid bars, we're going to use wires and connect them from one side to the next. So we have the same slots, the same slots as we have the same soft iron core that we have for the squirrel cage, except now instead of putting bars, we're going to run a number of wires through them and then tie them all up on the other side. So since we're using windings though, we could also connect them in different configurations like star and delta and so on. So this is a picture of what it would look like. So you see here, these are the soft iron, this is part of the soft iron core, and here you have the slots and the windings go through the slots. For the squirrel cage arrangement, the copper bars would go through these slots down here, and then they would all be connected with that bar on the end. With the wound rotor, however, we have the windings, and since these windings are all separate, we could connect them in star and delta and whatever we want. We could also short them all together, just like a squirrel cage. So, but one of the advantages is that we could connect them in typical three-phase arrangements. Now, while the squirrel cage is not accessible to the outside, there are no terminals or anything because there are no windings, everything is shorted together. With the wound rotor, we could actually bring windings out of the rotor and we could connect them to the outside, and that is what is typically done. So you'll have here slip rings. Notice not split rings like for the DC machine. Remember, for your DC machine, you had the brushes, and the two brushes were connected to a single split ring. Here we have each phase on a different ring, and the reason for that is simply these rings allow you to connect a stationary system to a rotating system. So the ring rotates, but it maintains contact with a stationary external system, and you could connect resistors to this, or you could also connect a power supply. And the version of this that is used for generation in the in wind turbines and so on is called a doubly fed induction generator. So that is basically it for the construction of the machine. By now you should be able to describe how the stator is oriented, talking about the displacement of the windings at 120 degrees apart, and also the displacement electrically at 120 degrees apart. And you should complete that exercise for homework and show how you could get a constant rotating magnetic field from it. And you should also be able to distinguish between wound rotors and squirrel cage rotors. So next we will look at how we develop the equivalent circuit for the machine.